We're going to start by reviewing binary addition. Let's look at an example. Here I have 104 and I'm adding minus 16. Now if you remember, we start from the right and we add each position and we propagate carries to the next position. Now here I've shown all of the carries. I've shown not only the 1 carries but also when I have a carry of 0 into the next position, and that's going to be important in a minute. In this example I've got 8-bit positions, and the carry out of a bit position is the carry in for the next bit position, whether it's a 0 or whether it's a 1. Now if you look at this, this is an example of modularity, where each bit position is treated the same way. So in every bit position I have the same inputs and the same output, and the inputs are the 2 bits that I'm adding, let's call those A and B, as well as the carry in from the previous position. And the outputs are the sum, the result in this position, as well as the carry out to the next position, which becomes the carry into that position. Now let's build a full adder circuit. A full adder is full because it takes a carry in as well as producing a carry out. And it has 3 inputs. It's a combinational logic circuit with 3 inputs, A, B, and carry in, and 2 outputs, the sum S and the carry out C sub out. Here's a truth table. It's a combinational logic circuit. We can describe it by its truth table, showing the inputs A, B, and C in, and the outputs S and carry out. Now, we've done enough addition so far that you should be able to verify for yourself the values for S and C out in every position. Verify based on what you know about binary arithmetic that those are the correct values for each of those. Now we can build the circuit just like we did before by using inverters, by using AND gates, and by using OR gates. So here's the circuit. I have my 3 inputs, A, B, and C in. I have a number of AND gates which collect all of the 1s in every row for S and for carry out. And then I have a number of OR gates, and I have 4 OR gates for each because for each of S and C out, I have 4 1s in the truth table. Now you'll notice I have this gate in the middle here where I take 1, 1, 1 as the input. And that's used for both carry out and for sum. Well, if you notice the last row of the truth table, we have 1s in both of those positions for S and C out. So we don't need to generate 2 different, replicate that AND gate. We can just use that 1 AND gate and just feed its result to both C out and S. Now it can be tedious to draw out all of these gates. So instead of drawing those out, we can represent a full adder by this circuit symbol. So this is just a handy symbol that we're going to use. So this is, you can think of this as a 1-bit adder. I have my 2 inputs A and B for the 2 bits I'm going to add. I have the carry in from the previous position. I have the result in this position, S, and then I have the carry out to the next position. Now we're going to use this adder to build a larger adder of however many bits that we need. For example, we can build a 4-bit adder. Now a 4-bit adder, let's take an example. I have 1, 1, 0, 0, and I'm going to add 0, 1, 1, 0. Now in the rightmost position, we treat it a little bit differently because we don't have a carry in. So what we're going to do is we're just going to force a 0 into that position. So we're going to make sure that carry into that position is set to 0. And then we're going to just treat this just like we do normal binary addition. We're going to feed the carry out from one position into the next position to the left. And here's our 4-bit adder. So in the rightmost position, I've got my 2 bits A0 and B0, and I'm producing the sum S0. Now notice that the carry in on the right is set to 0, as it should be. And now what I'm doing is I'm connecting the carry out from this adder to the next full adder, just like we do with normal binary arithmetic. And finally, I just chain this together. This is called a ripple carry adder because you can think of the carry rippling through this circuit from right to left until we get the final carry out C4. So we can do this modular type of design where we take one simple circuit, this 1-bit adder that we've created, and we can just chain it together in this manner in order to create an arbitrarily length of adder. We can make a 32-bit adder the same way.